Welcome back to the 14th video about the Melexis MLX90363 Triaxis magnetometer. In the previous video, we failed again with one of the orthogonality, respectively phase correction parameters, this time with auth B1, B2. However, we successfully demonstrated the functionality of the filter parameter. KT, link in the description. In this video, I want to revisit that auth B1, B2 parameter, and I also want to demonstrate a practical application of the sensitivity mismatch parameters before we finally start with the 3D stuff that chip is capable of. Enjoy! But before we dive in, some errata. You probably remember that every time we looked at chapter 16.3.2 magnetic angle X, Z and Y, Z, I stated that this is for 3D measurement of the magnetic field angle, delivering us two angles. And that was wrong. You see, the main chapter here, 16.3, does state user configuration 3D equals 0. So no 3D measurement, 2D measurement, formula trimming parameters, selectivity mismatch, and auth B1, B2. My only excuse is that this is on, well, a separate page. Yeah, well, they could have put it here, but it's still my fault, okay? So both chapters here, 16.3.1 and 16.3.2, talk about 2D measurements of the magnetic field angle, and 16.3.1 talks about measurements in the plane of the X and Y sensor, while 16.3.2 talks about measurements in the plane of the XZ sensor, respectively YZ sensor. They could have written here OR instead of AND to avoid such a misinterpretation, but then it states in 16.3 user configuration 3D 0. So yeah, still my fault. Anyway, we know that the auth cell bit controls if auth XY or auth B1, B2 is applied to correct any phase errors. We also know from the block diagram of the digital signal processing that the whole auth B1, B2 processing is disabled if 3D is 1. So yeah, 3D is 0 here, remember. With that newfound understanding of these two chapters here, I'm suspecting now that the application of auth B1, B2 is not only dependent on the setting of the auth cell bit and of course the 3D bit, but also on the setting of the MAPXYZ parameter. You see up here where we're just measuring the angle in the XY plane, MAPXYZ is supposed to be always 0. While down here, if we measure the angle in the two other planes, MAPXYZ is always not equal to 0. Yeah, we will try that out later. I also extended the reverse engineered signal processing in our sketch a little bit. I introduced a new function, DSP MAPXYZ, that maps our X, Y and Z signals to the passed as references, of course, B1, B2, B3 signals according to the active setting of our MAPXYZ parameter. And it's just a big switch statement that assigns the values of our X, Y and Z variables we pass to the according B1, B2, B3 variables we also pass here. In the loop, I have now, besides our x, y, and z variables, also new b1, b2, b3 variables. And I also introduced a delay of 15 milliseconds here. That's just so one full rotation of our sensor will fit onto the screen. After we received our XYZ data, we still store the X, Y, and Z values in our X, Y, and Z variables. But then I use the DSP MAPXYZ to map our X, Y, and Z values to our B1, B2, B3 values. And from now on, I'm no longer using the X and the Y value, but instead the B1 and B2 value to do the rest of the already existing processing. So I first apply here our DSP sensitivity mismatch to B1, B2. Then I calculate our alpha in degree using our DSP marker 0 alpha degree, using B1, B2 as inputs. And when printing out the stuff, I not only print out our raw Y and Z values. You remember we are now rotating in the Y and Z plane, but also our processed B1, B2 values. And that's unchanged. I print out the alpha angle we calculated and the alpha angle that the chip calculated, and then our zero line, min line, and max line. In the setup, I first make sure that our orthogonality select, our orthogonality B1, B2, our select sensitivity mismatch, and our sensitivity mismatch are set to their respective default or preset values. Then, for a first experiment, I changed here our fixed virtual gain to 25. Reason being, the magnet is now a little bit further away from our chip than before. And I update here MAPXYZ to B3, B1, B2. That is, X is now mapped to B3. That is, for 2D applications, we can forget about it. Y becomes the new B1 and Z becomes B2. I also changed the serial print here for the headings in the serial plotter. So first I have here now YZ instead of XZ, and I inserted here B1, B2. For our next experiments, I also modified our test rig here. So the magnet is no longer directly connected to that axis and rotating over the YZ plane of the sensor, but it's now rotating here on this axis. That's the magnet here. You see a metallic blink now and then, and now it's rotating in the YZ axis of the sensor. And that's how the whole thing looks on the serial monitor. So first we have here our Y, respectively B1 signal in blue and green. Very nice, a sine or a cosine. And then we have our Z, respectively B2 signal in red and orange. Also a sine or a cosine with a much larger amplitude. Why the Z sensor picks up a much larger amplitude reading, I explained that in the basics video. Card here, link in the description. Anyway, our angle readings, both the one we calculate and the one returned from the chip, are quite distorted because of the discrepancy between the amplitudes of our two signals. But there is a cure for that. In part 12, card here, link in the description, we saw the effect of the select sensitivity mismatch and sensitivity mismatch parameters. They're currently here on their default values, but let's comment that out and instead activate down here some settings I choose according to the amplitude mismatch we saw. So first, our B2 signal was larger than our B1 signal. So we select sensitivity mismatch to multiply our sensitivity mismatch factor with the B2 signal. And then I choose a sensitivity mismatch factor of 0.55. So we are now multiplying the B2 signal with 0.55. And yeah, I fiddled around off camera a bit to get to that value of 0.55. You can see the difference on the serial plotter right away. So now we have here two distinctive lines, red and orange, for our Z and our B2 signal. The red line is still the same, so the Z signal with a relatively high amplitude, but we multiply that now by the factor of 0.55 and get that orange B2 line, which has now more or less the same amplitude as our YB1 signal. And as a result, our angle reading, the one we calculated and the one returned by the chip, is much more linear. Yeah, there's a little bit of distortion left, but it's much, much better. We can now also test if the auth parameters have any effect, because MAPXYZ is no longer 0, that is B1, B2, B3, but has now a value different from 0, B3, B1, B2. So let's comment out here the default values and instead use these here. That is, I'm setting auth cell to B1, B2 and auth B1, B2 raw to its maximum value of 255. And we see that we see nothing. So the angle calculated by us without any auth calculations included is still identical to the angle returned by the chip, which is supposed to do that orthogonality phase error correction stuff, which is obviously not doing. And I'm at the end of my line here. I reviewed the code. I didn't find any fault in my code that would cause especially the auth parameters not to work. Maybe some viewer likes to actually download my code and have a look for him, herself. Maybe him or her can spot an error that I'm just not seeing. I don't know. Please leave me a comment. Pretty please. Now, let's go 3D. Please note, if we activate 3D, so set 3D to 1, that is true, the whole digital processing here is deactivated. And we're using two formulas here to calculate an alpha and a beta angle to characterize the 3D, sorry for the vertigo, the 3D direction of the magnetic field. These two formulas for the alpha and the beta angle of the magnetic field are given again in a more readable form in chapter 16.2 magnetic angle formula of the datasheet. Please note again, parameter 3D has to be set to 1. That is true. Let's first try to understand what these formulas do. And I want to start with the numerators of these two fractions here. Both numerators, so square root of k alpha times b3 squared plus kt times b2 squared and square root of k beta times b3 squared plus kt times b1 squared, have the same form. You have two expressions here squared and added, and then you take the square root of it. So square root of a squared plus b squared. Most of you will have already recognized that as the Pythagorean theorem that describes the relation between the three sides of an right-angled triangle. In its easiest form, it's written c squared equals a squared plus b squared. If you take the root of that, you get c is equal the square root of a squared plus b squared. If you draw the whole thing into a coordinate system with the axes a and b, c gives us the radius of a circle that goes through the point where b and a intersect. A and B being for the alpha angle, of course, B2 and B3, and for the beta angle, B1 and B3. Please note that there's an infinite combination of A and B values that give us a circle with a certain radius. So we really lose all information about B and A, and we are just left with a radius of a circle. In 3 dimensions, we get something like that. So we have two circles at a 90-degree angle, and yes, the other halves of the circles are below my bench. And one circle is in the B1, B3 plane. By default, that would be the XZ plane. And the other circle is in the B2, B3 plane. By default, the YZ plane. Of course, both circles can have different radii. Now, let's handle the arcus tangens part of these equations. So, alpha is the arcus tangens of the radius we calculated from B3 and B2 divided by B1. And beta is the arcus tangens of the radius we calculated from B3 and B1 divided by B2. Or more general, angle alpha is the arcus tangens of A over B. B being the adjacent side in a right-angled triangle to our angle alpha, and A being the opposite side. And again, we can draw that into a coordinate system with the axes B and A. And I'm using this time a small b and a small a to avoid confusion. So B would be usually our B1 or B2 axis, and A is the radius either calculated from B3 and B2 or B3 and B1. And this gives us an angle over the B1, B2 axis in the B3, B2, respectively B3, B1 plane. And please note that the datasheet says that these angles are extended across B1 equals 0 and B2 equals 0 and are at a maximum 180 degrees. So angles between 0 degrees and smaller than 90 degrees would be given if B, that is B1 and B2, are positive, and angles greater than 90 degrees up to 180 degrees would be given if B, that is B1 or B2, are negative. If B1 or B2 are 0, which you cannot calculate with an arcus tangens because you would divide by 0, we are at exactly 90 degrees. Again, looking at it in 3D. We have here our alpha angle measured above the B1 axis, and that depends on our signal strength on B1 and the radius of our B2, B3 circle we calculated. And then here above the B2 axis we have our beta angle, and you have to extend these two lines here up to the height of our B1, B3 circle. In other words, if that is our B1 axis, usually X, and that is our B2 axis, usually Y, then the angle of the magnetic field is given by the angle over the x-axis and over the y-axis. And that's exactly what we want from a joystick. We want a signal for Y and we want a signal for X. Let's go over the sketch to test all that. And I will save this time two versions of that Arduino software. First is called 14.1. This was the previous sketch, and that one will be called 14.2. I renamed the function DSP marker 0 alpha degree to just a DSP 2D alpha degree. Yeah, just a little bit of housekeeping here. We are not using that function currently. Anyway, I have a new function here, DSP KALPHA KBETA KT, which gets the MLX object as a reference and the values of our B1, B2 and B3 channel, and as references passed variables KALPHA B3, KBETA B3 and KTB1 as well as KTB2. These are the products, of course, with, for example, KALPHA times B3. And that's exactly what that function does. It calculates all these products. I will not use these products actively in that sketch, but I want to have access to all these products in the future. I have two more new functions, DSP 3D alpha degree, which gets as an argument a KALPHA B3 as a float, KTB2 as a float, and B1. And it just calculates the alpha angle in radians using the arcus tangens 2 function, as we have seen in the datasheet. And I return the whole thing, of course, not in radians, but really in degrees. And DSP 3D beta degree is exactly the same. It gets passed, of course, a KBETA B3 and KTB1 and B2. It does the arcus tangens 2 calculation according to the datasheet. And I return the result in degrees. In the loop, I have now all these variables KALPHA B3 to KTB2 added as floats, and I have now also a beta degree angle, also a float. And I'm no longer requesting here an alpha angle, but now the 3D alpha beta angle. In the section where we actually receive our raw XYZ data, I've added the function DSP, KALPHA, KBETA, KT to our DSP sequence, and I'm now calculating here the alpha degree and the beta degree using our DSP 3D alpha degree function and DSP 3D beta degree function, passing here our products. In the serial print section, I now print out no longer XYZ, but B1, B2, B3, which should be identical currently. And besides the alpha degree scaled up by a factor of 10, also the beta degree scaled up by a factor of 10. And besides the received get alpha degree from the chip, also scaled by a factor by 10. In addition, the received get beta degree scaled by a factor of 10. And I'm printing out a 0 line and a 180 degree line. Yeah, 180 times 10 is 1800. In the setup, I first reset all parameters we used before to their default values. And then I set a fixed gain of 3. Again, I experimented a little bit before to get to that fixed gain. And I update 3D to true. I also changed the headings here for the serial plotter to now B1, B2, B3. Our own calculated alpha and beta angle, the alpha and beta angle returned by the chip, our 0 line and our 180 line. I also rebuilt the test jig again. First of all, I'm no longer using the diametrically magnetized magnet here, but a more conventional magnet. So that end of the magnet here is north and the other end that sticks inside the plastic is the south. Furthermore, that magnet now is always at an angle and it rotates all around, slowly but surely. That basically simulates a circular motion with our joystick over the Y and X axis, with of course the magnet being at the end of our joystick here. And as always, the look onto the serial plotter. So we have here blue, red and green, our B1, B2 and B3 signal. Please note our B3 signal has a quite large amplitude here and is always in the positive range, which is understandable because, yeah, our magnet always points down with its north from the top. Sorry. Then we have here blue and red, our B1 and B2, which is our X and Y signals, which are around the 0 line. Yeah, because we point from left, right and back, front. So that's all okay. And then we have here our orange alpha and dark green alpha from the chip signal. That's this line here. And the first good news, it's changing and both are identical. Same is of course true for our own calculated beta angle here in lilac, and in light blue the beta angle returned from the chip. That's that line here. And they very roughly do what you would expect. However, they are obviously totally distorted. The reason being, we haven't adjusted all these K parameters, K alpha, K beta, and KT, and we need to adjust them to get proper readings out of that thing here. But that's for another video. That's it for today. As mentioned before, in the next video in this series, we will look at these K alpha, K beta, and KT parameters and how to adjust them that you get out proper angle readings in your 3D, respectively, joystick mode. Till then, bye.